Well, welcome to Lecture 2. In this lecture, we're going to discuss a topic called bases. The singular form is basis, and we'll define that in just a moment. But I want to approach that definition by starting with something familiar. So what we'll say is the following. We're going to let V be a vector space and the associated scalars will be, let's just say, R, the set of all real numbers. As we said before, our scalars will usually, in this course, be the set of all complex numbers, but in some cases you could also use a smaller set, just the set of all real numbers. So here in this example, we'll just say we have the set of all real numbers. It really doesn't matter. So we're going to let V be a vector space, and the associated scalars will be all real numbers. And now we will define a set X in the following way. Let V1, and maybe I don't need to use the overbar quite yet. Let V1 and V2 be two particular vectors. Let me say here, I want to be real careful my point is clear, so I'll say two fixed vectors in V. Then we're going to let X be the set of all linear combinations of V1 and V2. Now, what does that mean? Okay, what that means is that X is the set of all vectors V such that V is equal to alpha V1 plus beta V2 for any alpha and beta in the associated set of scalars, which in this case is R. So the way you should think about this is, as I said, V1 here, V1 and V2 are fixed, but here alpha and beta can vary. Both of them can assume any real value. So obviously, if we let alpha, if we let alpha range over the set of all real numbers, and also let beta range over the set of all real numbers, we will get a very large, obviously, and in fact an infinitely large set of vectors here, and that set of vectors we will call X. And now we want to ask the question, is X a subspace of, let me make the vector space be script V so that we can distinguish between the script V for the vector space and the V here for vector. Okay? So is X a subspace of V? That's the question that we would like to ask. And as usual, the way that we will answer this is to look at our two properties. First is X closed under vector addition. Okay, that will be our question. So now, actually, I think at this point, before going any further, I'd like to encourage you to turn off the video and to think about this question for yourselves and try to figure it out alone first, and then come back and see if you agree with the reasoning that we present here on the video. Okay, so I hope you've had a chance now to look at this problem and think about it a little bit. And so, as I hinted before, what we're going to do is to look at the two properties that all subspaces must have and see if X also has those properties. So the first one is closure under vector addition, and the way we test that is as follows. Remember, we'll pick any two vectors in X, and if we can pick any two vectors in X and the sum of those two vectors is also in X, then we say that X is closed under vector addition. So we'll say let W1 and W2 be any two vectors in X. And then we have to ask, is W1 plus W2 in X? That's going to be what we're going to check now. Okay. Well, if let me put it maybe instead of saying if, I'll say since W1 is in X, we know that there must be some scalars alpha 1 and beta 1 such that W1 is equal to alpha 1 V1 plus beta 1 V2. Now, how do we know that? Well, remember, X is the set of all vectors that can be written in this form, alpha V1 plus beta V2, for any alpha and beta in R. So when we say that W1 is in X1, that means that W1 can be written in this way, that there's some alpha and some beta such that W1 is equal to that alpha times V1 and that beta times V2. And so I'm just going to call those that particular choice alpha 1 and beta 1 to help us remember that those are the choices of alpha and beta that go with W1. Okay? So W1 is equal to alpha 1 V1 plus beta 1 V2. And likewise, for the same reason, W2, or let me put it this way. Likewise, there must be scalars alpha 2 and beta 2 such that W2 is equal to alpha 2 V1 plus beta 2 V2. So far we've just used the fact that W1 and W2 are vectors in X, plus the fact that every vector in X is a linear combination of V1 and V2, to express W1 and W2 in terms of V1 and V2. So now we get to this question. Is W1 plus W2 in X? let me repeat the question here. Is W1 plus W2 in X? Well, W1 plus W2, according to what we have just seen, is equal to alpha 1 V1 plus beta 1 V2 plus alpha 2 V1 plus beta 2 V2. And all of this can be regrouped as alpha 1 plus alpha 2 times V1 plus beta 1 plus beta 2 times V2. So W1 plus W2 can be written in this form. Now remember, alpha 1 and alpha 2 are scalars, likewise beta 1 and beta 2. So when we take alpha 1 and alpha 2, these are just two real numbers, and we know when we add up two real numbers, we get another real number. And likewise here, when we add up these two numbers, beta 1 and beta 2, we get a real number. So both of these are just scalars. They're also just other scalars in the set of all possible scalars, which remember is the set R. The associated scalars will be R. So what we've shown here is that indeed W1 plus W2 can be expressed as a linear combination of V1 and V2. So W1 plus W2 is an element of X. So X is indeed closed under vector addition. But of course, that's not all. We also have to check for closure under scalar multiplication. And so let's do that next. And if you did not get part 1 correct before, then I encourage you, now that you've seen the solution to part 1, to stop the video and see if you can do part 2 on your own before referring to the video. Okay, so now let's see how that would go. We'll start off as before. We'll let W1 be any vector in X and lambda be any scalar. And so we ask then, is lambda W1 in X? Well, W1 is in X implies that there are real numbers alpha 1 and beta 1 such that W1 equals alpha 1 V1 plus beta 1 V2. This is just what we had before. So lambda W1 is equal to lambda times alpha 1 V1 plus beta 1 v2. But that can be rewritten as lambda alpha 1 times v1 plus lambda beta 1 times v2. And now we think about it. Okay, remember alpha 1 and beta 1 were real numbers. Lambda is a real number, and so when we multiply a real number times a real number, we still get a real number. So this is a real number multiplied by v1 plus a real number multiplied by v2. And so indeed, this is an element of X. So X is indeed closed under scalar multiplication and since X has satisfied both properties, let me say this way just so there's no confusion. So since X satisfies both properties, X is a subspace. So that is the conclusion of this first example for today, and it gives us a little bit of review of the idea of subspace, which we touched on last time, but it also has brought up a new idea that somehow, this idea of linear combinations. And so this is going to lead us. Let's look at another example of this. Note that an example of the situation above is the following. Now, this is just one example or one illustration of what we were doing in example 1. We could, for instance, let V could be R3, and as we said, we've already said the scalars are all real numbers. And let's pick for our vectors V1 and V2. Let's pick two particular vectors. We're going to let V1 be the vector 1, 0, 0, and V2 be the vector 0, 1, 0. Now, if we do this, can you see what X is? If we define X as above, in other words, X is the set of all linear combinations of V1 and V2, then note that X is simply R2, or the set of all vectors in the XY plane. Now, if that's not obvious to you, just think about it this way. Remember that x is equal to the set of all vectors v such that v is equal to alpha v1 plus beta v2 for any alpha and beta that are real. So in this case, x becomes the set of all v such that v is equal to alpha times 1, 0, 0 plus beta times 0, 1, 0 for any alpha and beta that are real. But now that can be written even more compactly as the set of all v such that v is equal to alpha, beta, 0 for any alpha, beta that are real numbers. And then you can clearly see from that that that's just the xy plane, because we're saying here that the x component can be any real number, the y component can be any real number. The only restriction is that the z component is 0. So this set x does coincide with the xy plane, and which is also referred to as R2. So another way of saying this that you will hear some people use sometimes is they will say that the two vectors that we've chosen here, 1, 0, 0 and 0, 1, 0, generate R2. Or another way of saying it that you'll see sometimes is they span R2. Any vector in R2 can be written as a linear combination of these two vectors. Now let's talk about another idea. So let's first put in writing what I just said. So v1 and v2 generate or span R2. These generate and span are just two words that you will see frequently in linear algebra texts. Now let me try to introduce now another idea. Suppose v3 was equal to maybe the vector 1, 2, 0. If we define a set y to be the set of all vectors v such that v is equal to alpha v1 plus beta v2 plus gamma v3, where alpha, beta, and gamma are any real numbers. If we define y in that way, then what is the relationship between x and y? Now, let me make sure you understand my thinking here. Remember that x was a set of all vectors that could be written as alpha v1 plus beta v2. Okay? But now we're going to let y be the set of all vectors that can be written as alpha v1 plus beta v2 plus gamma v3. So what is the relationship between x and y? Well, certainly we see that any vector that is in x is certainly also in y, because let's say that, let's just pick a vector in x. Since x is a set of all linear combinations of v1 and v2, okay, maybe we'll have 5v1 plus 3v2. Well, clearly 5v1 plus 3v2 is also in y, because we could pick alpha equal to 5 and beta equal to 3 and gamma equal to 0. So any vector that's in x certainly will be in y, which makes you think that possibly y is bigger than x. So let me put this down. I'll say certainly any vector in x is also in y. But is y bigger than x? In other words, is there any vector in y that is not in x? Okay, so this is an interesting question here. Is y bigger than x? We know that anything that's in x is certainly in y, but are there any things in y that are not in x? Okay, well, let's now, for those of you who've had a little bit of linear algebra, you probably recognize that right now I'm beginning a discussion of an idea called linear independence. And we should be familiar with this idea in this course. But, if you're losing me a little bit, don't be too concerned. Just try your best to grasp this idea. And certainly don't hesitate to ask me questions either by email or in class if you, have some trouble with it. But in order to try to answer this question of whether or not there's any vector in y that is not in x, I want to re-examine the definition of y. So let me write it down again. Y is equal to the set of all v such that v is equal to alpha v1 plus beta v2 plus gamma v3, where alpha, beta, and gamma are any real numbers. Okay? Now, let's go ahead and substitute here. This is alpha times 1, 0, 0 plus beta times 0, 1, 0 plus gamma times 1, 2, 0, where alpha and beta and gamma are any real numbers. Now, when we write this way, there's a trick we can pull, and let me show you how this goes. Okay, we bring down those first two terms, but now for the third term, I'm going to do the following. I'm going to recognize that vector 1, 2, 0 is the same thing as 1, 0, 0 plus 2 times 0, 1, 0. Okay? Now, let's see what comes next. Okay, now look very carefully at what I've done. Here, okay, we started off with the definition. Y is a set of all linear combinations of V1, V2, and V3. And so here I've just made it explicit in going to this line what V1, V2, and V3 were. And here in going to this line, I've just brought down my definition of V1, brought down my definition of V2, but now the crucial step is that this V3 itself could be written in terms of V1 and V2. And in particular, this V3 is equal to V1 plus 2 V2. And so I'm writing that down here in this step, and then when I go from this step to the final step, okay, I'm going to gather together all the coefficients of 1, 0, 0, which is alpha and then gamma here. So alpha plus gamma times 1, 0, 0, and all the coefficients of 0, 1, 0, which is beta here and 2 gamma over here. And notice now that it's important that you understand what we've accomplished. We have now seen that y is really just the set of all linear combinations of just these two vectors, because that third vector that we had really could itself be written as a linear combination of V1 and V2. So really we didn't achieve anything extra by adding in that extra vector in the definition of y. So you see that in fact this expression right here is just exactly equivalent to our definition of x. So our answer is, so y is equal to x. Okay? Now, let's say here, it is clear from the fact that y equals all linear combinations of V1, V2, and V3, that V1, V2, and V3 generate or span y. But y equals x. So V1, V2, and V3 also generate or span x. But we have also seen above that V1 and V2 alone generate or span x. That is, V3, the addition of V3 does not change the set generated. In fact, now let's just look at this. 1 0 0 0 1 0 1 2 0 2 5 0 7 8 0 E pi 0 negative 1 7.8 0 also generates x. And if you're wondering about that, now just look. See, 1 2 0, that's the same thing as V3, but that can be written in terms of V1 and V2. This could be written in terms of V1 and V2. This could be written in terms of V1 and V2. Likewise this. Likewise this. So the addition of any of these extra vectors doesn't really change the set generated. So we come up now with the following idea: basis of a subspace equals a minimal, any minimal set of generators of the subspace. So, for instance, 1 0 0 0 1 0 is a basis for R2. But 1 0 0 0 1 0 1 2 0 is not. This set does generate all of R2, as we saw above. But it's not minimal, because as we have already also saw, these two vectors alone generate all of R2. Now you might be wondering, how do we know that this is minimal? How do we know that we couldn't take one of them away? Well, you can try it, and you'll see if you took the second one away, you would just get the set of all vectors that have both y and z equal to 0, and so that would just be the x-axis. And likewise, if you took away the first one and had only the second one, you would get only the y-axis. So you can't take either one of those away. You need both of those. And so this is a basis for R2, but this one is not. And now let me ask you a tricky question, and I'm going to ask the question, and then I really do urge you to stop the video and try to answer it yourself. Let's try this. Is 1 negative 1 0 1 1 0 a basis for R2? I want you to look at that very carefully and see what you think, and then we'll all look at it together. Well, the way that I'll proceed with this is the following. Let's consider any vector in R2. Now, if a vector is in R2, it must have the form x, y, 0. So now, can x, y, 0 be expressed as a linear combination of 1, -1, 0 and 1, 1, 0. In other words, do the vectors, or rather than do, I'll say, can the vectors 1, -1, 0 and 1, 1, 0 be used to express any vector in R2? That's what we're asking here. Okay, so let's see. X, y, 0. We're going to try it out. We'll hope that it works, and we'll see. We'll suppose that it's equal to alpha times 1, -1, 0 plus beta times 1, 1, 0. Now we have to find out if there is an alpha and a beta that would work. Well, this would be equal to alpha plus beta, beta minus alpha, 0. Now for this vector on the left-hand side to be equal to the vector over here on the right-hand side, we must have the following. Alpha plus beta would have to be equal to x, and minus alpha plus beta would have to be equal to y. And if you look at that for a moment, you see that that would imply, if you add these two equations together, that beta would be equal to x plus y over 2. And then if you substitute that expression for beta into the, you express this, put that in here, and then work with that, and you'll see that alpha is equal to, let's see, x minus y over 2. Now let's check this to make sure. So we're saying that any vector x, y, 0 in R2 can indeed be expressed in terms of 1, -1, 0 and 1, 1, 0 in the following way. It's equal to x minus y over 2 times 1, -1, 0 plus x plus y over 2 times 1, 1, 0. And I believe that you can see that that does, in fact, work out. Let's just check it. So the first vector would become x minus y over 2, and then negative x plus y over 2, 0. And the second vector would be x plus y over 2, x plus y over 2, 0. And now when we add them up, we get 2x over 2, 2y over 2, 0, or x, y, 0. So this proves that by picking alpha equal to x minus y over 2 and beta equal x plus y over 2, we can express any vector x, y, 0 in R2 as alpha times 1, negative 1, 0 plus beta times 1, 1, 0. So 1, negative 1, 0, 1, 1, 0 definitely generate R2, but is this a basis? And the answer is yes, because if we took either one of these vectors away, like if we took this vector away, then we just get all multiples of this vector, which would be a straight line. In fact, it's the line y equals negative x and z equals 0. And on the other hand, if we take this vector away and just look at all multiples of this, we get the line y equals x and z equals 0. But if we take the set of our linear combinations of both, that's when we get all of R2. So this set is minimal, and so it is indeed a basis. I'll say yes, because it both generates R2 and is minimal. So what we see here (1, 0, 0) and 0, 1, 0 Okay, so we'll conclude by saying this. 1, 0, 0, 0, 1, 0, that collection of vectors is a basis for R2, because we saw that any vector in R2 can be written as a linear combination of these two vectors, And likewise, this collection of vectors is minimal. If we took either one of them away, then we could not get all of R2. Similarly, these two vectors form a basis for R2 for the very same reason. We saw that any vector xy could be written, xy0 could be written as a linear combination of these two vectors by choosing alpha and beta correctly. But likewise, if we took either, so that generates all of R2, but on the other hand, we couldn't take either one of these away because then we would just be left with a straight line and not the all of R2, which is a space, a plane. So this set is minimal and it generates all of R2, so it's also a basis. But this collection right here is not a basis. It does generate all of R2. We saw that. But this vector is somehow redundant. It is not really necessary. In fact, and I'm not going to do this, but it's not, although it looked like this one was redundant, to be honest, we could take out this one and use these two vectors, 1, 0, 0, and 1, 2, 0. That would be a basis. Or we could have 0, 1, 0, and 1, 2, 0. That would be a basis. We just don't need all three of these. And so what we would find out if we pursued this idea further, which I think is not really appropriate right now, we might look at it later, but this falls more into a linear algebra course, so we won't pursue it much further. But what we would find is that any basis for R2 would have two vectors in it. In fact, the dimension of R2 is 2, and the dimension of a subspace, in fact, is simply equal to the number of vectors in its basis. And so once you know the dimension of a subspace, you know immediately how many vectors are in its basis, and any set of vectors that has more than that cannot possibly be a basis. One more thing here before we stop is the following. Let's maybe ask, what is a basis for R3? Now we've already noticed from the example right here that the basis for a subspace is not unique. There are infinitely many bases for R2, and likewise for R3 there are infinitely many bases. Can you give me a very simple one? If not, stop the video for a moment and think about it. But I think if you'll give this a moment's thought, you'll realize that one particularly easy choice is 1, 0, 0, 0, 1, 0, 0, 0, 1. Any vector in R3 can be expressed in terms of those three. And notice that it starts out 1, 0, 0 and 0, 1, 0. It starts out just like this one, but then the addition of this extra vector here, see, this vector, unlike 1, 2, 0 here, this didn't add anything new to what we already had, really, because 1, 2, 0 could be written in terms of these two. But the addition of this vector to the set does add something new, because this vector cannot be written in terms of these two. You see, it has a non-zero z component. Both of these have zero z components. So it doesn't matter what scalars you choose, there's no way you could pick some scalar times this vector and some scalar times this vector and get a vector that would have a non-zero z component, because both of these have z components equal to 0. So we need, if we want to have all of R3, if we want to generate all of R3, we need to have some vector here that has a non-zero z component. And the easiest way to do it is to throw in this one. So this is a very simple, this is frequently called the standard basis for R3. And again, there are infinitely many bases for R3, but how many vectors are in every one of them? And the answer must be 3, because the dimension of R3 is 3. So I hope that that begins to make the idea of basis a little bit clearer. And now we will look at some problems concerning this notion. Okay, so now let's look at the problems. And by the way, in case you're wondering, I know that these first 2 lectures have both been over 50 minutes. My plan in the future is that the lectures will be a bit shorter, more like 40 minutes. But since this beginning material is review for some of you, I thought I would include just a little bit more. But anyway, now for the problems. In problem 2.1, I ask you to identify all the choices, and there may be more than one. Identify all the choices which are bases for R2. So A is the set of these 2 vectors, 1, 0, 1, 0, 1, 0. B is the set of the 2 vectors, 1, 1, 0, and 1, 2, 0. C is the set of the vectors 1, 1, 0, 1, 2, 0, 1, 3, 0, and D is the set of the 2 vectors 1, 0, 0, and 2, 0, 0. And by the way, for R2 here, I am talking about the XY plane, just as I was in the lecture. So this is the plane Z equals 0, or the XY plane. Okay, in 2.2, I want you to identify all choices which are bases for X, which is the set of all vectors in R3 that have Y equal to 0. Instead of having Z equal to 0, as was the case up here, we're now looking at the set of all vectors, 3-dimensional vectors that have Y equal to 0. And so again, you have some choices down here, and you should pick all of them. Again, there may be more than one. All of these that are bases for the subspace under consideration. And then 2.3 will be given in class, but I think it is sort of a tricky one, so I'm going to give you a hint to think about this. Say X is equal to the set of all vectors in R3 such that X plus 2Y plus 3Z is equal to 0. Could you find a basis for that? Well, I'm going to tell you that the dimension of that set, this is a subspace, and the dimension is 2. So the basis, any basis for it, should have 2 vectors in it. So think about that, and then I'll give you a similar problem in class. So that concludes lecture 2, and good luck.